So right now we have the first of the two talks this afternoon by Emile Richard who's currently at Stanford University, and he will be talking about structured array factorization.
Okay, so thanks for the invitation. It's very good to be here to present this work I did mostly with Andrea Montanari, my current advisor, and also there is a piece of work with my former collaborators in Paris. So what I'm going to talk about is structured array factorization. So I use array factorization because I'm going to talk about matrices, but also a little bit about tensors, so higher order arrays than order 2. And so for motivating the problem, I'll start telling that there are some problems in which different types of variables interact together. And if you linearize the problem and try to solve a linear regression kind of problems, you're not going to catch the real structure that is in your data. So in some cases, it turns out that you have to take into account these kind of structures that you have in your data. So matrix factorization problems are typically of that sort. So it's a problem where your unknown can be written as a matrix, and you're looking for a factorization of that matrix into the product of two matrices which have specific structure on which we have a specific prior knowledge. So these kind of factorizations, the standard factorizations are like SVD or things like this, but there is a way larger variety of these factorizations, and that come out of various applications. So the first application, and very popular application, is the clustering application, where you need to you want to separate your data into several groups of uniform points. So in that case, you can represent your matrix X that contains samples per row as the product of UV transpose, where U, the left factor, is a factor that contains the information of which cluster each data point belongs to, and the right factor contains the centroids of your clusters. So this is an approximation of your data with the factorization. Another very popular application, which attracted a lot of attention after the Netflix challenge, is to build recommender systems. So in that case, you want to represent a set of users and set of items that they scored in the same low-dimensional feature space. So this also, when you write the problem, you see that it comes up to doing a factorization of your score matrix. There are other applications where you have different sorts of data that are interacting together. So this is also an application which is my personal favorite these days, where you have a large number of neurons, and from which you acquired recordings using a multi-array electrode, and you want to understand the structure of the neuron population using those multiple time series. So this is also a problem where different types of quantities are interacting together, and to capture the whole information that you have in your data set, you need to look at the problem as a tensor factorization problem. So other problems are like dictionary learning, where from a data set of images or any kind of data, you want to learn small sets of structures in order to do denoising, so to remove so this is named in-painting. So you take an image, you add some random noise on it, and using dictionary learning, you can remove that noise. When you formulate this problem, it also ends up to be a matrix factorization problem, where you have different kinds of priors on the various factors. So on one factor, you have a sparsity prior, so you want each of your elements to be expressed as a small number, as a linear combination of a small number of your dictionary elements, and the dictionary elements also need some special regularization. So a problem that is orthogonal to this one is a sparse PCA problem, where you want to select a small subset of your variables that explain the best the variability of your data. And this is useful because you cannot look at all the elements of your covariance matrix because there is too many of them. You need to not only to look at a low-rank representation, but inside the low-rank representation, you need also to do a selection variable-wise to select some of them that are explaining the best the data. Other applications are like community detection or subspace clustering and also topic modeling. So all of this just to say that there are many reasons to motivate this kind of thinking about the data as being an array, a matrix or a tensor, and trying to factorize that is the natural way of trying to reduce the dimensionality for doing prediction or having better interpretation of the data. So in all these problems, we try to express the unknown as the outer product of vectors of a few, so a few number of terms that are like outer product of vectors, and on each of these vectors, we may have some prior knowledge. We want them to be nice in some sense. So being nice can mean being sparse, being non-negative, being etc. So these are the type of problems we are going to be interested in, and there are two questions. The first question is, when does it work computationally? When can we compute such a factorization? And the second question is, when does it work statistically? So we are trying to, in simple models, to discuss these two questions. And then see how much we can extend this. So I'll start by talking about PCA. So it's something that all of you probably know way better than me. But it's just good to have this in mind for just to contextualize what we are going to do after. So we have some number of observations that are vectors in Rn. And what we are looking for is a direction which is a one-dimensional projection of this data such that this quantity is maximized. So this quantity is some kind of variance. So it's the sum of the variabilities, sum of squares of inner products of the input data with this vector, which is the unknown. So it turns out that we can rewrite this problem this way just by concatenating the input data. And this is known as the PCA, Principal Component Analysis problem. So what I'm going to discuss about is several extensions of this PCA problem. One is what we call the cone constraint PCA. So we have some extra prior knowledge about this vector that is the principal component that we model as being this vector should belong to some cone in addition to be on the unit sphere. I'll discuss a bit more on one of these cones, which is the non-negative orthant, because it has good motivations, and also we have finer results on that. And then I'll quickly discuss what happens in case of tensors, so higher order arrays of order 3 or more. So the first part is joint work with Andrea Montanari and his student Yash Deshpande. So remember that we had this problem, we had this PCA problem, and as I said, we have an extra prior knowledge that's on the unknown vector, and we want to know if this extra prior knowledge can bring us any information, can be useful, can be leveraged statistically in order to refine the detection. And also, if you have such a prior knowledge, for instance, if you know that your vector is non-negative, the vector you want to find, or if you know in which orthant it lives, then how can you use this information? So to tackle this problem, it's good to look at the simplest possible model. So the simplest possible model is that you have your input data are represented as a sum of signal plus noise. And the signal is going to be one simple vector. So V0, the V0 is the vector that we want to estimate. and the noise is going to be, so we normalize everything in order to have beta representing the signal-to-noise ratio. This is the signal, and U0 is a vector that also has L2 norm equal to 1. So these normalization choices are made in order to make the model simple and to have beta represent the signal-to-noise ratio. So this can be written as, again, in matrix notations rather than having all these vectors, x1 up to xn. We can write the whole model as a matrix problem. So capital X here is a matrix of size capital N by small n. Capital N is the number of observations, and small n is the dimensionality of the data. And so the goal here is to recover the vector V0, or to find a vector V that has a non-zero inner product with V0. So we want to be as close as possible to V0. In some cases it's possible, in some cases it's not. It turns out that if the number of observations is way larger than the dimensionality of the data, we can easily recover. So here is the case where the number of observations is larger than the dimension of the data. We can easily recover the vector V0. In the reverse case, we can't say anything. And in the middle, in case where small n and big N grow together, then it really depends on the ratio between these two and the value of the signal-to-noise ratio. So from now on, I'm going to change a little bit the model and talk about a model which is similar in notations. And the previous case, we can always switch to the previous case by comparing beta rather than comparing it to 1, but compare it to the square root of the ratio of dimensions. But from now on, we focus on a symmetric model where the observation matrix X is given by beta V0 V0 transpose plus Z. So and the problem we are interested in is to maximize this term, which is named the Rayleigh quotient, subject to L2 norm of V being 1 and V belonging to some cone. So some specification. Beta, again, is the signal-to-noise ratio. V0 is the signal that lives in that cone that we know in advance and has a norm equal to 1. And Z is going to be a symmetric noise matrix, so we can build it as the sum of two matrices of size n by n, which have entries IID distributed from a Gaussian distribution. And we have this normalization factor here, which is going to be quite important to balance, to see the right balance between the signal-to-noise ratio and the dimensionality of the data. We call lambda 1 of x, comma c the value of this problem, and v1 of x, comma c the maximizer. So what do we know about this problem? There is a bunch of things we know already in case C is equal to Rn. And so just shortly review these things, and because I want to redo the proof in that case using the techniques we use to tackle the other problems. And the reason for that is that the theorem I'm going to state is not new. You know it already, but the proofs are going to be declined in the case of cone constrained PCA and in the case of tensors, and it gives a good intuition why we get the results we get after that. But so I'll start with okay. So basically, what we know is that in case the cone is the whole space, the eigenvalues of the data matrix, in case we don't have any signal, are going to be distributed as a semicircle. So this is what Afonso discussed already yesterday. And we know also that if we have a little bit of signal until 0.9999, something like this, the distribution is not going to change. The distribution of the eigenvalues is still going to be the same. So between -2 and 2 and following this semicircle law. But as soon as the value of the signal-to-noise ratio gets larger than 1, suddenly you see one eigenvalue pumping up. And the value of this eigenvalue is going to be beta plus 1 over beta. So as soon as beta is larger than 1, we get this value, which is the one I represented here. So here is the theoretical prediction, and that's the value obtained numerically in a simulation with n equals 1. So here is the theorem. The theorem, which was proved using various tools in many papers that I don't have place to cite all the papers that discuss this theorem, but this is a bunch of those. So the theorem not only gives the value of lambda 1, the value of the first eigenvalue of the spiked covariance matrix, of the spiked matrix, but also gives the value of the inner product of V1, so the leading eigenvector with the truth V0. So basically we are seeing a phase transition as 1, which is that if beta is larger than 1, we get a non-trivial eigenvector associated to this eigenvalue. But if beta is smaller or equal than 1, we get an orthogonal eigenvector associated with the eigenvalue 2. So the way we can obtain this theorem, so there are various ways, but this is the proof technique that we use to prove the theorem we have for the non-negative PCA. I'm just reviewing the proof because that gives an intuition why we obtain those results, but I'm not going to go in all the details of those results because they would require to write very long math formulas, and it's not the most important. The most important is to get the intuition of where the phase transition is going to take place. So the important thing is not the values, the important thing is the location of the phase transition. And everything is simpler in the case where we are considering plain eigenvectors, so on. And so for proving this theorem, we first prove an upper bound on the value of the problem that we do using Sudakov-Fernik inequality. So it's a standard inequality on Gaussian processes. And for obtaining a lower bound that matches the upper bound, we use approximate message passing. So it's a constructive proof that together with giving us a sequence of vectors that achieves the upper bound, it also gives us an algorithm that can be used in order to build those eigenvectors. But the algorithm is not new. You'll see that the algorithm is more or less the one that you guess. It's some kind of power method. So for the first part, which is the upper bound and the value of the problem, we use an extension of the Sudakov-Fernik inequality, which is the following. So if you have two random vectors, two Gaussian random vectors, x and I, where element-wise they satisfy this inequality. So the expectation of each entry of x is smaller than the expectation of the corresponding entry of y. So this is the extension of Vitale of Sudakov-Fernik inequality. In the standard inequality, the two random processes have to be centered. So that's the only thing is added here. So if we have this condition plus the difference of the expectation of the difference squared satisfies the same inequality, then the expectation of the max of the first process is upper bounded by the expectation of the max of the second process. So in our case, we are going to be interested in these two random processes that are not indexed by a discrete number of elements, but by an element V that belongs to the unit sphere. So it turns out that the conditions of this theorem are satisfied. It just requires 2 lines of algebra to get it. And the conclusion is that the consequence is that the expectation of the maximum of x index v. So x index v is the value of the problem for each unknown vector v. So the expectation of this is upper bounded by the expectation of the supremum over vectors v of this quantity. So the good thing here is that once we wrote that, we can expand the vector, the unknown vector v in the basis of v0. So v0 plus an orthogonal component, and write basically that the value of the problem is upper bounded by the maximum over only a real number. So that's a more it's a way easier function to maximize of this real function. So the good thing with this real function is that you can find the maximum pretty easily. You just take the derivative and set it equal to 0. And it turns out that when you do the computation, you get that this value is always smaller or equal than beta plus 1 over beta, once beta is larger than 1. And the other good thing about this proof technique is that also when you look at what value of tau is maximizing this real valued function of tau, you get also that the inner product of v0 and v1 that you can express in terms of tau is going to be equal to exactly the quantity we wanted to get. So this gives us an upper bound on the value of the problem. And as I said, to get a lower bound, we'll use a constructive proof, which is based on using approximate message passing for this problem. So the basic way of obtaining the leading eigenvector of a symmetric matrix is by using power method, is by hitting a vector multiple times by the matrix and normalizing at each time if you want to have numerical stability, or otherwise you normalize only at the end. But basically you build a sequence of vectors as follows. Vt plus 1 is x times Vt. The only thing we add to get the so-called approximate message passing algorithm for this problem is to subtract a term, to subtract the previous term. And the normalization can go also here. You can normalize by the norm of Vt plus 1 at each iteration. But basically that's the only modification you have to do to the power iteration to get the EMP version of it. So I'll tell you right at the next slide why yes.
So, but do you have to scale it when you subtract it, or because otherwise you might get 0 already at
You don't start at 0. If you don't start at 0, you cannot get at 0.
Okay. So I guess my question is, you need to make sure that you don't subtract too much, right? Or
You normalize it. So if you want, you can write Vt plus 1/2 equals this, and Vt plus 1 is Vt plus 1/2 normalized by its norm. Or
so the norm of x is the same as the norm of Vt minus 1.
okay, so this is only for simplification. I didn't write the normalization, but otherwise you write ut plus 1 equals x Vt minus Vt minus 1, and Vt plus 1 equals ut plus 1 divided by norm of ut plus 1. Does it happen? Okay. If spectral, how can it happen? Spectral norm of x cannot be smaller than 1. With the normalization we took. Okay? Okay. Yeah. Yeah, you should initialize it at 0. If you initialize it at random, it works. Yeah. Okay. So a first step to see how the analysis work is to say, okay, let's say that we are given a vector which is tau, so again a real number, time v0. So v0 is the signal that we are looking for, plus plus noise. So this noise is a Gaussian random vector which is centered and has variance 1 over n. So if we multiply the input matrix x by this vector, we obtain another vector which is tau prime v0 plus g tilde. And here I made the assumption that g, so the noise that is on this vector that I'm hitting with the input matrix, is independent from the noise that is in the data. If I make this hypothesis, we can write it. We can write this. So this is again going to be a Gaussian vector. And tau prime is expressed in terms of tau like this. So it's a function of tau. The reason why I cannot repeat this reasoning on power iteration is that the vector g tilde is going to depend on z. And the reason why in AMP we added this memory term, so the right intuition to see why it's behaving this way comes from previous work of Andrea. You can read this book chapter, Graphical Models, Concepts in Compressed Sensing he has, where he explained it in case of least squares regression, in case of the lasso, why this term is going to give you independence when asymptotically when n gets large. But so basically, what is proved in our paper is that when n gets large, this the noise of the vector after hitting the input vector with the matrix is going to be independent from the noise of the matrix. Okay, so this is the effect of the memory term. I'm not going to go into the technical details of this. I'm not going to prove that, but just admit for the moment that it's true. And if you continue this reasoning, you get a sequence of real valued you get a sequence of real numbers tau index t that satisfies this iteration equation. So when you have a sequence like this, so we have tau t plus 1, which is a function of tau t. The natural thing is to plot the curve of f of t, f of tau, and to do the following. To take so you start at a point which is close to 0, because you start at a point which has an inner product with v0 that is of order 1 over square root of n. But you start say here, and you get this is the value of f of tau. This is tau, and over iterations, the inner product with tau is going to increase, and we end up at some point here, which is smaller than 1. Tau can be larger than 1, but tau over 1 plus tau square, which is the inner product with, so this is the inner product of v0 with v1. This is always smaller than 1. So basically in these plots, what I'm showing is this function for two different values of beta. We have the function for beta equal to 1. That's the blue curve here. And we have the function for beta larger than 1. So what you see here is that when beta is larger than 1, you're getting an intersection between the curve x equals y and the curve of this iteration function that is away from 0. And in case tau is equal to 1, or sorry, beta equals to 1 or beta smaller than 1, you get only an intersection at 0. This means that the sequence of vectors Vt is going to converge to a vector that is orthogonal to V0. Okay. And when you look at this function also, you can write a fixed point equation, which is tau equals to the value of the function, and you get that the value of tau over square root of 1 plus tau square, which is the inner product of V0 with V1, is going to be exactly the value that we expected. And the value of the Rayleigh quotient here, so this is the Rayleigh function in terms of tau, is going to be beta plus beta minus 1. So that was a very simple proof of the theorem that you guys already knew. Okay, so now I'm trying to surprise you. Now what happens if never we add a cone constraint to the to the PCA problem? So we add the constraint that the unknown vector V0 belongs to some cone, say a convex cone. We get in this case that the phase transition is not going to be to take place at 1, but it's going to take place at square root of the statistical dimension. So for this theorem, so we have the proof for several cones. We have the proof that this is tight for several cones. For some of the cones, so I mean, for the general case of a convex cone, we have a proof that this is going to be the upper bound, but the lower bound is going to be proportional to this quantity using a information theoretical result. For the non-negative orthant, we have a proof using AMP. So exactly the techniques I showed you before can be used for the non-negative orthant. For the circular cones, we have a proof using a lower bound, which is done analytically. But for the general cone, we conjecture that it is true, but we haven't yet proved it. So if you have ideas, share them. So what is the statistical dimension? I'm definitely not the right person to tell you what the statistical dimension is here. But it's a quantity which is close to the Gaussian width that Holger discussed about yesterday. So you can write the quantity as the expectation of the projection of onto this convex cone of a Gaussian random vector with variance identity over n. So this quantity is very close to the square of expectation of the maximum of z belonging to the cone of intersected with the unit sphere of z times a Gaussian vector. So the use of this quantity in compressed sensing and several other applications like denoising and demixing dates back to the work of Rudelson and Verchinin, and prior to that it was used by Tomczak and Pajar, if I'm not wrong. And it started, the first use in compressed sensing was by Stojnik in Caltech, and then their following results also followed by Caltech people. So it's mainly a Caltech toy. But it has been used a lot in compressed sensing, and we were very surprised to find this quantity being useful in a context which is totally different. So we found out that the phase transition for this PCA problem is also at the same place. So the good thing about it is that once we got this result, so we had we knew the value of the problem for, okay, if the cone is the whole space, we already knew that the phase transition would be at 1. But if the cone is the non-negative orthant, we know where the phase transition is going to be. We know also for subspaces or for circular cones, etc., and for a number of other cones which are often tangent cones to known norms. So the algorithm we can use to compute these constraint eigenvectors is very similar to power iterations by adding a projection step at each iteration. So if at each iteration you project the vector onto the cone and you repeat it a number of times, log n number of times, and the log n comes from the fact that if you pick the initial vector randomly, it's going to have an inner product of order 1 over square root of n with the signal. So after log n steps, you're going to get an inner product with the initial vector, which is of order 1 minus, again, the same quantity divided by the signal-to-noise ratio. And this works as soon as beta is larger than the square root of statistical dimension. This algorithm is parallelizable, and it can be used also. I mean, it can be generalized for non-convex cones, but in that case, we don't obtain this convergence theorem. We can only obtain convergence to local optima of the objective.
So why don't you need this
So here we don't use the memory term. Because if you want to write AMP, you need to have a projection that is a function you are applying element-wise to your vector. So for a general cone, it doesn't work, but for a non-negative orthant, it works because all you need to do is to take the positive part. Okay? So the projection to the non-negative orthant is by applying this nonlinearity. Okay, which element-wise to your vector. But for a general cone, you cannot write the projection as an element-wise function. Exactly. I don't know. Okay, so as I said, our favorite was the non-negative orthant. So one of the reasons was precisely this one, that the projection operator is separable. So, and also the other reason why it's our favorite is that also it has lots of applications. So there are many cases, like in genomic applications, where you want to select a subset of the data, or in some applications where signals are added and you know that they cannot be added negatively because it doesn't have any physical sense. There are cases like this where you want to use the non-negativity, also in topic modeling or clustering or the original use of non-negative matrix factorization to learn patches in images, etc. So the theorem we have about this is that as soon as, if beta is smaller than 1 over square root of n, you can find a sequence such that the inner product of the non-negative principal component with V0 asymptotically goes to 0. So you can exhibit such a sequence for any vector V0. So there is no recovery in the worst case. But as soon as beta is larger than 1 over square root of n, there exists a function. So this is a minimax kind of theorem, which says that there exists a function such that the inner product of the solution with the signal is always larger than this positive function of beta. So again, there is a phase transition here that occurs at 1 over square root of 2. So it's the one that we already discussed. It's the square root of the statistical dimension of the orthant. So the gain is maybe a bit disappointing because we are only gaining a factor of square root of 2. But still, if you're doing experiments and you're getting a result that is square root of 2 better than what you had before, it's already not bad. And also because this square root of 2 has a nice interpretation. So just numerically, to see what is happening, I generated some data using the symmetric spiked model. And I computed the leading eigenvector, so here V1, and the non-negative eigenvector, here I denoted it by V plus, and for various values of beta, and also for 3 different kinds of true vectors, true signal vectors that I generated. So here epsilon is denoting the sparsity of the vector. When the vector basically is getting very sparse, it gets harder to estimate. So the higher this inner product is, the better the estimation is. And when the vector gets dense, so when the vector is close to the middle of the orthant, it's easier to estimate it. So even for small values of signal to noise ratio, we're capable of estimating it. It's not surprising, because if the vector is in the middle of the orthant, you just take the vector all equal to 1, and you have a nice estimate of your own. And what we see here is that the phase transition for the eigenvector is occurring at 1. And the phase transition for the non-negative principal component is taking place at 1 over square root of 2, as we had predicted by the theory. And you can see it when the vector is getting the sparsest possible. So in the theorem we had here, these worst cases that we considered in both parts of the theorem, the worst cases are the vectors that are very sparse, because those are the vectors that are hard to estimate. You need to find where the support is. And as I told you, the analysis is done so on the upper bound by using Sudakov-Fernik inequality, and on the lower bound by analyzing IMP. So, and when you analyze IMP, the surprise that we had also a surprise on the numeric side, which is that, okay, this problem is a co-positive programming problem. So we know that this problem is NP hard. Somehow we have a theorem which says that if we run this sequence for a logarithmic number of steps, so logarithmic in terms of the accuracy we want to achieve at the end, here n is going to infinity, so the theorem cannot depend on n. We know that the sequence we are building is going to converge to the truth. And the cost of the algorithm is only by doing matrix vector multiplication, so the algorithm is very parallel. So the small difference that there is in the algorithm is that here we are using this non-linearity, the one that I plotted here. So it's only taking the positive part of the vector and setting of each element of the vector and setting the rest to 0. And the memory term that we use here is slightly different than just taking the non-negative part of the previous vector. It's using so it's something which is related to the derivative of this non-negative function. So it has the indicator. So it's the number of non-zero elements of Vt plus divided by a normalization constant. So the same kind of techniques has been used by Andrea and Yash to obtain a constant which is slightly better than 1 over square root of 2 for case of for the clique problem, and they conjecture that this constant 1 over square root of e is the optimal constant for that problem. So that problem is the setup of that problem is a bit different from our setup. It's not an AMP algorithm that they use. It's a message passing algorithm, so a plain belief propagation algorithm they used. But the constant is, okay, so 1 over square root of e is a bit smaller than 1 over square root of 2, so they can do a bit better. But the 1 over square root of 2 is already not bad for this problem. Okay, so if I have time, I can also discuss about tensors before switching to the second part of the talk. So, as I said at the beginning, we are talking about structured array factorization problems. So here the array is not a matrix anymore; it's a tensor, which is a table of numbers which can be indexed by k indices. So k is the order of the tensor. It could be larger than 2 if needed. So if you have k different types of quantities that are interacting together, you may record your data as numbers indexed by I1 up to IK. And here again, we can consider a model which is similar to the last one. So it's again a spiked model. We have a noise term here, Z, again indexed by the same indices. And we add a signal that is similar to the rank 1 signal we had before. So before the entry ij of the matrix was beta v0i v0j. And here we have multiple terms like this one, so plus noise, plus zij. So we assumed in the previous case that the matrix Z was a symmetric matrix with entries IID from normal 0, 1 over n. And in this case, we built such a matrix, which is going to be symmetric. So here there are k different indices. So the symmetry of this tensor can be obtained by adding up by building one first tensor G, which has n to the k independent entries, and applying all the permutations in the group of permutation of k elements to the indices of this tensor, adding up all those tensors and normalizing this by 1 over factorial k. And this factor is also here for convenience for further manipulations on this tensor. So here the model I wrote is a symmetric tensor, which is a rank 1 tensor plus a symmetric noise tensor. So both the signal and the noise part are made symmetric in this case. And the goal, again, is to estimate the signal V0 and we are going to discuss in which cases it's possible and in which cases it fails. So it's known that most of tensor problems are NP-hard, and it's known that tensor PCA is an NP-hard problem. But you see here that if beta goes to infinity, so basically if you're given a rank 1 tensor, it's very easy to estimate the vector V0. You just do an inner product. You just write the product of the tensor in all the directions except one with one random vector, and the vector you're going to obtain at the end is going to be proportional to the signal. So there is a good reason to believe that if beta is large enough, you are still capable of saying things about it. Despite knowing that, okay, the problem in general is a very hard problem. So again, we use the same techniques as before. We get an upper bound and we try to build a lower bound that matches. But everything doesn't work as well in case of tensors, and I'm going to tell you what surprises we got when we started working on this. So there is an information theoretical argument which tells us that a beta of order of 1. So here when I write order, it's for a fixed k, the order in terms of n going to infinity. So for beta, a constant function of k, we know that statistically it's possible to estimate the vector V0. I'm going to say what this constant is going to be. And we know that numerically when beta is larger than a function of n, which is n to the power k minus 2 over 4. So if k equals 3, if we are looking at third order tensors, for beta larger than n to the 1/4, we are able to recover a vector that has a non-zero inner product with the signal. And in the middle of that, we conjecture that it's impossible to estimate it. It's impossible to have a numerical method to estimate that the vector V0, or to build a vector which has a non-zero inner product with V0. So the details of this work are in a NIPS paper I have with Andrea. So first, let me talk about the upper bound. And so we got the upper bound by, so we tried the previous technique of Sudakov-Fernik, and right after I'll show you why why we didn't use that, because it gives us a loose upper bound for small values of the signal to noise ratio. But in order to get an upper bound on the noise process, we looked at the physics literature that Andrea knew, since he has a physics background. So the paper is the work of Hoffinger, Czerny, and Ben Arous. We were talking about Ben Arous previously. So they really? Okay. So they have this work on p-spin glasses. So p is the order of the tensor. Here is k, so it's like looking at k-spin glasses. And they are capable of characterizing the value of the problem for various values of k. And they are also capable of saying that if how many local minima the problem is going to have. So if you write by what the problem is going to have, I mean, they have a function that they name h. So h of v is v. So this is the tensor power inner product with z. They know they state that this function has exponentially many local maxima in terms of the variable v, and they know what the expected value of the maximum of this function is. So it turns out that the expected value of the maximum. Okay, and again, if I put the absolute value, it's going to be a norm. It's going to be what we call here the operator norm of the tensor. This is going to be characterized by a sequence of real numbers that grows as square root of k log k. So if k equals 2, we get the value 2 that we already knew. But when k gets larger, we get a sequence that grows as square root of k log k, and here I computed the precise values of this sequence. We know that the limit as n goes to infinity of the expectation of the operator norm of the tensor is exactly mu k is if k is even, and is bounded above by mu k is if k is odd. And this is only known for symmetric tensors. If the input tensor is not symmetric, we don't know any result on the operator norm of the noise tensor. So one direct consequence of this is that as soon as the value of beta is larger than mu k, the maximum likelihood estimator is going to give us a good solution. So as soon as beta is larger than mu k, we get a non-zero inner product with the truth with high probability. And this is also due to the fact that we took a Gaussian noise which concentrates well around the expectation. If we use the Sudakov-Fernig technique, we get an upper bound which is of the order of k at beta equals 0. So we know that this upper bound is loose, but the upper bound gets tight for beta larger than a value which is of order of k. So when beta is larger than k, the upper bound we get using that is going to be correct. So. And again, we try to build a lower bound using power iteration or AMP kind of techniques. And in this case, we also face some difficulties. And the difficulties come from the fact that I'm going to a bit detail by comparing the iteration function we obtain here with the one we obtained with k equal to 2. So I'm not going into the details of the computation, but basically for doing the power method, you need to write the product of the tensor in all in k-1 directions with one vector v at each iteration. It's the analogous of writing a matrix times one vector. So, but when the tensor has a larger order than 2, you need to write it in k-1 direction of the tensor. So it's basically written as a sum on all the indices except 1 of x by the corresponding indices of v. So by using the normalization choices we made on the noise tensor, we can see that when you hit an unknown vector with the tensor, the value of the inner product of Vt plus 1, so Vt plus 1 is the sequence built using a power iteration kind of algorithm. The value of the inner product is going to grow as beta times the value of the previous guy, power k minus 1. So when k was equal to 2, this k minus 1 is equal to 1. So therefore, we get an iteration function which is around 0. It's going to have a linear behavior, and the slope is given by beta, by the value of the signal to noise ratio. But when k gets larger than 1, this function is going to have a polynomial behavior which is going to be flat at 0. So the bad point here is that when you start at a point close to 0, it's going to the sequence is going to converge to 0, and therefore you end up computing a vector that is orthogonal to the truth, because the inner product with the truth is going to converge to 0. So if we write the AMP kind of sequence that corresponds to that power iteration, we get so the so-called state evolution, which is the value of tau t plus 1 iteratively written as a function of the value of tau index t. We get these functions that, as I mentioned, are flat close to 0, and therefore if you start at 0, you're going to, or if you start very close to 0, you're going to end up at 0. But the other side of this computation is that if you plot the rest of this function, you see that if you start at a point which has a large enough inner product with the signal, you're going to improve on the point you started with. So it's not completely hopeless, and also in cases where the dimension n is small, there is a way to build a vector which has a non-trivial inner product with the signal. So here in these plots, I plotted the state evolution functions, and so here k equals 3, and this value where the function crosses x equals y is characterizing the minimum side information, or the minimum inner product you need with the signal in order to start power iteration and converge to a non-trivial, to a better point than the point you started at. And these are the corresponding Rayleigh function curves, which say that, okay, if you start at this point, if you are on the blue curve, you start at this point, you're going to end up here. And this corresponds to the black curve here. So it means that if you start at this point, you're going to increase the Rayleigh function until reaching the maximum of the Rayleigh function. So there is a one-to-one correspondence between these two curves. The point where the iteration function is hitting the x equal y is this is like a first order condition that these two functions are equal, and this corresponds to hitting a maximum on the Rayleigh functions. So how do we obtain a non-trivial initial point for the tensor problem? One way of doing it is by flattening the tensor. So you take your tensor and you build a matrix out of it. So if the tensor was of order k, you build a matrix that we denoted here by m index q, which is of size n to the q times n to the k minus q. So in case k equals 3, you can see your tensor as a cube, and it's just by taking slices of this cube and building a long matrix out of the tensor. So in case of the non-symmetric noise, we can take a noise matrix V that is not symmetric. When you flatten that noise, you're going to obtain a matrix which has IID entries And we normalize the variance of the entries to be of the order of 1 over n. So basically, this matrix is going to have an operator norm of order of 1 over square root of n times, so the matrix has size n to the q times n to the k minus q. So we can compute the expected value of the operator norm of the flattened noise tensor. It's going to be of this order. One conclusion we can get from this is that in order to make the noise small, you need to take k close to q because you need to make the value of the operator norm of the noise small. So for this, you need to get q of the close to k over 2, as close to k over 2 as you can. I mean, it has to be an integer. So if k is even, it's going to be k over 2. Otherwise, it's k over 2 plus 1/2. So this argument is telling us that as soon as beta is larger than this value, which is the operator norm of the noise for the optimal choice of q, then by using the results we know on PCA, you're capable of computing the PCA of this tensor and keeping only track of one part of the principal component, or by repeating this operation several times on that tensor. As soon as beta is larger than n to the to something which is close to what we were expecting, we get a nice initial vector for starting the power iteration. And we have some heuristic arguments which are saying that n to the k minus 2 over 4 should be enough. So the summary of our results is that if you start with a random initialization, as we were doing for regular PCA, we need the signal-to-noise ratio to be of the order of n to the k minus 1 over 2. Whereas if you start with the unfolding kind of algorithm, so you unfold several times your matrix and compute the PCA, you need n to the k minus 2 over 4. So both these bounds, we prove them rigorously, kind of loose bounds, but we have heuristic arguments to believe that these bounds, the true value of the bounds should be these ones. We don't have a rigorous proof for them yet. We proved that the maximum likelihood estimator can be computed as soon as beta is of the order of square root of k log k. So of the order of 1 in terms of n going to infinity. And using information theoretical argument, we know also that this value is optimal. And we conjecture that the problem is intractable for values of beta between 1 and n to the k minus 2 over 4. So just very quickly, numerically, we did some experiments for the various values of n. So we see that when n is small, we are capable of computing a vector which has a non-zero inner product with the truth. But when n goes to infinity, all the methods start to fail. So here, all the methods, we have the tensor power iteration with random initialization, which is the worst we are doing in all these different cases. And all the others are, so here we have the unfolding in dotted blue curves, and some cone-constrained PCA where we use the fact that when we unfold the order 3 tensor, the left factor is going to be a positive semi-definite factor because it's VV transpose. And we took all these algorithms and we did tensor power iteration right after to see that we get an improvement. And when we plot these different curves, we can superimpose them for various values of beta divided by n to the 1/2 and beta divided by n to the 1/4. And this is it's by looking at these numerical values that we started conjecturing the exponents that I announced here. So this is the end of the first part of the talk. I went a bit, talked a bit too much. We'll finish it a bit earlier on the rest, okay?